Let's continue on 3.3. Last time we discussed the first derivative and the use of the first derivative to find the increasing and decreasing interval, local max and local mean. Today we're going to discuss the second derivative and using that to find the behavior of the graph function f. So first, I want to start with two definitions. We say for a given graph, a function f, say if the graph of f lies above its tangent line, then over an interval I, then the function there is concave upward. And if the graph lies below tangent line, then that part of the graph is concave downward. So here there are two shapes. And if you look at this left one, if I pick a point and draw the tangent line, what you see is the tangent line is below the graph, or you can say the graph is above, so the graph is above the tangent line. That means this is a concave upward. Anywhere that you pick, any point, the tangent line always is below, or the graph is above the tangent line. You can think about that. If this happens, then this part, this graph is concave upward. And on the other side, if you look at the other part, you draw the tangent line at any point. What you see is the tangent line is above the graph, or the graph is below the tangent line. If that happens, then the graph is downward, concave downward. It's just, you can think about the shape of ball, either upside, upward or downward. You can cut off a corner of it. You can cut a corner of it. It's still upward in this section. On the other side, you can do the same. If you cut up this part, this is still downward. So of the ball, whatever, if it's the upward section, the graph would be concave up. If it's the upside down ball, then you have a concave downward. But this is a basic definition based on the tangent line. Okay. One more definition that lies between these two. So let's say you have a curve that is like concave down, and then it's connected at some point to a concave upward. Everywhere here, tangent line. Everywhere here, the tangent line is above the graph, or the graph is below the tangent line. On the other side, the graph is above the tangent line. At this specific point, what you see is the tangent line crosses. That means where the change and the concavity happens. This is a concave down connected to a concave upward. That specific point, when there is a change in the concavity, from concave up to concave down, or from concave down to concave up, this point is what we call it an inflection point. It's the point that represents change in the concavity. It's either changing from up or down, or down to up. So here you could have, again, the curve could change something like this. At this point, this is an inflection point, because you say change from up to change downward. And if you have concave up connected to another concave up, something like this point does not consider as an inflection point, because there is no change in the concavity. This is not you have two concave upward graph and you connected those. It doesn't really call an inflection point. The inflection point happens only if you have a change of concavity from up to down. So that's what we call an inflection point. I wanted to mention it before through the graphing, because here's the definition later on. Definition of an inflection point, before I mention the concavity test, is a point in the domain is called an inflection point. There is change in the concavity at that specific point. We call it point P. Okay, so what is the concavity test? Before I mention the test, maybe we should look back at the graph. Let's say here you have this point, and you look at the slope of the tangent line. What do you see is a negative slope. If you go a bit forward, what you see is a positive slope. If you continue, the slope stays positive, but you see that the slope gets larger and larger. So what happens is the slope is increasing from negative, then it gets close to zero, then zero, positive, and go on. And slope keeps increasing. That means the derivative is increasing. If you're dealing with a concave upward graph, the derivative is increasing. If the derivative is increasing, that means the next derivative must be positive. Because last time we had, if a function was increasing, then the derivative of it was positive. So if f prime is increasing, then the derivative of that must be positive. That means the concavity test is if the second derivative is positive, then you have a concave upward. If the second derivative is negative, on the other side, if you look at the derivative, you have an increasing graph, decreasing derivative. The slope of this tangent lines are keep getting smaller. It turns to a negative number as you go on. But if the derivative is decreasing, it's not the function, it's the derivative that is decreasing, then the next derivative must be negative. So this is for the derivative, but originally for the function, if the second derivative is negative, that means the function was concave down. The curve is concave down. This is what we call it the concavity test. It's similar to the increasing and decreasing test, but it's for the second derivative. It tells you the information about the original function. So if the second derivative is positive, then you have a concave upward. If the second derivative is negative, you have a concave downward graph. Here's an example of it. Given this function f, we want to find the interval, find the concavity interval, maybe I should say. Find the concavity of the f. Where is concave up, where is concave down, and find the inflection point as well. Inflection point. By the way, inflection point, they ask you for a point, give a coordinate x and y. Don't forget that. Anytime you see a point, you're asked to find the coordinate, both x and y. So given the function f, to find the concavity, you should find the second derivative. So first I find the first derivative. It would be 4 times 1/2, which is 2x cubed, minus 2 times 4x squared, which is 8x. 3 will disappear. Second derivative would be 6x minus 8. Okay, 6x squared, sorry. Okay. What we're gonna do is we want to find something like critical number, but for the second derivative. So we want to find first where second derivative is 0. This is the first part, because you want to draw the number line and do the similar behavior that we did for the first derivative. So I will set the second derivative equal to 0. 6x squared minus 8 equal to 0. What you get is x equals 4/3, so x equals plus or minus 2 divided by square root of 3. So this is a critical number for the first derivative, not for the function, for the first derivative. I don't want to mention it as critical number for the first derivative, so it's a choice for the inflection point. How about that? The possible inflection point. Okay, draw the number line, but this number line is for the second derivative. It's important to consider this second derivative next to it. What are the critical points for the first derivative? What are the solutions that we found is -2/√3 and +2/√3. Now what we do is we pick test point in each section. Here I'll pick -5. Actually I can pick -2 is good enough. Here's 0 and here's +2. Just make sure that these numbers belong to the corresponding interval. I'll place -2 into the second derivative. It's not going to the first derivative. Second derivative, use test point -2. You'll get 6 times -2 squared is 4, 24 minus 8 is 16. So you'll get a positive value. If you replace 0, you'll get a negative number. If you replace 2, you'll get a positive value. The point negative 2 over root 3 and 2 over root 3, the second derivative here was 0. So I'm going to put 0 there. Okay, what does this plus or minus sign tells us? The plus or minus sign for the second derivative tells us about the concavity. That means positive sign means concave up. The way to show it, you can draw a ball. Say this is the concave upward. Negative means concave down. Not increasing and decreasing because it's the second derivative. It's a concavity. Concave down, positive means concave up. Again, these test points are useless at this point. You don't need the test points. It was just to figure out the sign. This is kind of useless. We don't really need these. Okay, so what is the concave up and concave down interval? Concave up and concave down. Concave up happens to be at negative infinity to negative 2 over root 3 and union 2 over root 3 to infinity. Concave down one happens to be negative 2 over root 3 to 2 over root 3. This is where the concave up and concave down happen. And then they ask you about the inflection point. Where do you see change in the concavity? Concave up to concave down. It happens at this point. Concave down to concave up happens at this point. The 2 points you found as the critical number for the first derivative are basically choices for the inflection point. They may or may not be the inflection point, but those are the points that are possibly going to be the inflection points. So if they ask you for the inflection point, since they say point, you mean you have to have x and y coordinate. X is given 2 over root 3 and negative 2 over root 3. How do you find the y value? You go back to the original function. You replace it into here. I don't want to replace 2 over root 3. Actually, I can do that. 2 over root 3 to the power 4 would be 4 over 9 minus 2. You can calculate that one. I don't want to do that. It's adding up fractions. F of negative 2 over root 3. You should calculate these two. Okay, so that would be the inflection point. You have 2 of them. You have the graph would kind of looks like, the function would kind of look like this. Concave down, concave up, and it changes to concave down, and it changes back to concave up. This is how the graph of the function f looks like that. This point is at negative 2 over root 3. This one happens at 2 over root 3. There's a local maximum, minimum, and local maximum, another local minimum. Okay. You should combine this second derivative with the first derivative. You can find out exactly where these points happen as well. Okay, this is about the concavity and inflection point. It's very similar to the first derivative, but you draw the number line for the second derivative. And here's some information that I wanted to mention is sometimes they give you a graph and they say, okay, now approximately graph f prime in the second derivative. What you can see is, given the function f, I picked 2 examples actually. Let's draw first one from the left hand side graph A, and this is graph B. So let's do this example for graph A. We want to find out the graph of f prime first. So the function starts from 0 up to wherever this point is. The function is increasing up to 1. Up to this point, the function is increasing. What does it mean? That means the derivative, first derivative, must be positive. So up to 1, here's 1. you should have a positive f prime. So f prime must be here. Positive f prime. From 1 to 2, what do you see is decreasing? You have a negative derivative. From 2 to 3, still is a negative derivative because the function is still decreasing. I just wrote negative, but basically it means the function has to be in this area. From 3 to 4, the function is increasing. So it should be, derivative must be positive. From 4 to 5, the function is still increasing, this section. And from 5 to so on, still the function increasing. So it should continue to follow this behavior. So what I'm going to do is, I'm going to start from somewhere here, around 0, and say the function is in the positive area, and then it goes to negative area. So somehow comes here. At 2, what you see is change in the concavity. That means at 2, it turns back, because at some point it has to cross and go to the positive. Here. What happens at 4? At 4, there is change in the concavity again. That means the derivative will be decreasing up to this point. Then again, here's a change in concavity at 5, but it still is above. So again, starts to increase. Something like this. It doesn't really matter how you graph it. Just important that consider these concavity changes as well. It's an approximation. It's not supposed to be exactly what do you see. Okay, maybe I should try. So here, the slope of the tangent line, let me show you this. The slope of the tangent line at this point is smaller than the slope of the tangent line at this point. That means the y value for the derivative must be smaller than the y value there. So maybe I should fix this. Say here it will decrease a bit and increase, so on. Kind of, you should adjust how you graph this. Maybe it's kind of turn into something like that, whatever it looks like. It's just the sections that are important. Go from negative to positive, positive to negative, and so on. And how about the second derivative? You can look at the second derivative as well. What do you know about the second derivative? Second derivative tells you about the concavity. So here is the concave down. The graph is concave down up to this point, up to point 2. So the graph has to be negative up to 2. The graph has to be negative. From 2 to somewhere, the graph is concave up to 4. The graph is up here. And here is concave down. So from 2 to 4, the graph is concave up. That means the second derivative is positive. It should be somewhere here. And this is up to 4. From 4 to 5, if you look at the graph, from 4 to 5, graph is concave down. And after that, the graph is concave up. So it's the second derivative is negative, then the second derivative is positive. Second derivative is negative. Then here, after 5, the second derivative is positive. So the graph starts from a negative section, goes to the positive section, then it turns back to the negative, then goes back to the positive. And whatever it looks like, it doesn't really matter after that. Okay, so it's important that these points, you'll see there is change in the concavity. These are supposed to be the inflection points. 2, 4, and 5 is where the change happens. Change in the concavity, inflection points. Okay, it kind of becomes local maximum and minimum for the first derivative, this inflection point, because the next derivative would be 0. I don't want to confuse you, but just look at the slope of the tangent line for the first derivative, for the increasing and decreasing for the first derivative, for the second derivative, look at the concavity. You can try to do graph B as well. Here, again, decreasing up to 1. So first derivative is negative. And from 1 to 3, the function is increasing. Here's 3, increasing. And from 3 to 4, the function is decreasing. So it should be negative. And from 4 to whatever, the derivative is increasing. So it should be positive. If you look at the point 4, what you see is like a break point. So the derivative does not exist at that point. So kind of you should consider this point as an open circle when you draw the derivative, graph the derivative. I'm going to show you how to draw it. First, start from negative, go to positive, and then you have to come back to the negative. Here's what you should know. At 4, since you have a break point, there is like a sharp corner. Remember, the derivative do not exist at the sharp corner. So I'm going to make it an open circle because the derivative does not exist at that point. And I will continue graph the function. This point here where the maximum happens is basically where there is change in the concavity. It happens at 2. Not specifically, don't need to be too specific, but it's good to know. And the second derivative relates to the concavity. Where is the graph concave? Up here. So up to 2, the second derivative must be positive. Up to 2, second derivative is positive. This is for the second derivative. And from 2 to 4, second derivative was negative since it was concave down. 2 to 4. And after 4, second derivative is still concave down. So after that, still second derivative is negative. So you have a positive turn into negative, and it still stays in the negative. We don't know how it stays. I'm going to draw it this way. Maybe draw it this way. But here's again, the derivative did not exist at this point, so I'm going to use an open circle. Since you stay in the negative, you don't need to go back to the 0 and say, okay, let's continue that way. Maybe it will go up. Maybe this is the case. An open circle and continue this way. We don't specifically know, but I'm going to draw it this way. Say, okay, I don't have that much information, but I'm expecting the concavity and the second derivative to be infinite at this point, actually. But let's not get very precise about how the graph would look like. It's just the above or below the x and y axis. X-axis is good enough. So this is graphing the first and second derivative based on the original function. Sometimes they give you extra information. They give you the number lines for the first and second derivative, and they ask you, now can you go back and graph the function? So here, let me mention this example as well. Let me shift it up a bit so we have more space. This is, oh, okay, kind of messed it up. This was 2, this is f double prime. Okay. So in this case, they ask you to graph function f, and what is the given information is the number line for first derivative and second derivative. For the first derivative, the number line tells you that the function is decreasing here and increasing and decreasing. So you have a local minimum at 0, local maximum at 4. And the second derivative means you have a concave upward graph in this section and a concave downward here. And the point 2 is an inflection point. And here, given some of the values, these are a bunch of points, and they tell you the derivative is 0 at 0 and 4. That means these two were critical numbers. 0 and 4 were critical numbers. These are the critical numbers. Okay, so let's graph the function f. So maybe I should focus mostly on the right hand side since the given informations are after 0. So here, first start with the points. 0, 0 is given. F of 0 is 0. f of 2 is 3, so here's 2 and 3. F of 4 is given 6, so here is 4, and f of that is given 6. Okay. So what do we know? The function is decreasing up to 0. And decreasing how? Decreasing is, this is 0 here. 0 is less than 2. Decreasing in concave up. So up to 0, function has to decrease concave up. So somehow like this. And from 0 to 4, the function has to increase. But from 0 to 2, increases concave up. And after that, it's still increasing, but concave down. It changes the concavity. Because here is 4. From 0 to 2 is concave up. And after that, it's concave down. The point 2 is an inflection point. Again, this is a combination of both graphs. You can draw a table and put them together. Okay, here's f prime, here's f double prime. Here are the points 0, 2, and 4. These are the given points on the number line. F prime was given negative. Then after that, from 0 to 4, it was positive, so increasing. And after 4, it was decreasing. Second derivative was given concave up. To 2, after 2, it turned concave down. So what does the graph look like? F is a combination. Decreasing concave up, it will look like this. Increasing concave up, it will look like that. By the way, you cannot draw it this way because it's not increasing on the left side. So increasing concave up would look like that. And then increasing concave down would look like this. And decreasing concave down look like that. So it means I should draw the curve connecting these 4 pieces. Here's the left one. This is the middle one from 0 to 2. From 2 to 4. And you see 4 is a local maximum. We expect a local maximum. Then it's decreasing and concave down. So somehow like this. So this is a sketch of the graph of f. Y equal to f of x. Not too accurate, but it's accurate enough to see the local maximum and local minimum and the inflection. Okay, this is good enough for this section as well. These are the type of questions that you will see. Drawing this table is kind of useful as well. If you can draw the table, maybe you should do that. If you can draw this table. Find the f prime section, the second derivative, and combine them together. Given the increasing and decreasing, how do you expect the graph to look like? This is kind of useful, this table. Okay, I'll stop at this point.